Hello everyone, welcome back to the channel. Today, we're diving deep into one of the most foundational topics in natural language processing, word embeddings. Specifically, we'll be focusing on two of the most popular and powerful techniques, Word2Vec and GloVe. If you've ever wondered how machines understand the meaning of words and convert them into numbers that AI can actually work with, you're in the right place. By the end of this video, you'll have a solid understanding of both techniques, when to use each one, and how to implement them in Python. So let's get started. So first things first, what exactly are word embeddings? Word embeddings are numerical vector representations of words that capture their meanings, semantic relationships, and context. Now, let me show you why this is such a big deal. Traditionally, we used something called one-hot encoding. Look at this. Each word is represented as a sparse vector with all zeros except for one position. So, cat is 1000000, dog is 010000, and so on. The problem? These vectors tell us absolutely nothing about the actual meaning of the words. According to this representation, cat and dog are just as different from each other as cat and king, even though we know that cats and dogs are both animals and should be more similar. Now, look at word embeddings. Instead of sparse vectors, we get dense vectors. Numbers like 0.2, 0.8, 0.3, and here's the magic. Words with similar meanings end up with similar vectors. So, cat and dog will have vectors that are closer together in this high-dimensional space, while king may be further away. The embeddings actually capture semantic meaning. The key insight here is similar words have similar vectors in high-dimensional space. This is absolutely fundamental to how modern NLP works. Now, you might be asking, why do we actually need these embeddings? What problems do they solve? Let me give you 3 critical reasons. Number 1, numeric format. Computers don't understand words. They understand numbers. Word embeddings convert text into a numerical format that machine learning models can actually process and learn from. Number 2, semantic relationships. Embeddings capture the actual meaning of words and the relationships between them. This is crucial for tasks like translation, sentiment analysis, and chatbots. Number 3, dimensionality reduction. Remember that sparse one-hot encoding? If you have a vocabulary of 100,000 words, that's 100,000 dimensional vectors. Embeddings reduce this to typically 100 to 300 dimensions while actually adding more information. That's powerful. But here's where it gets really cool. Check out this famous example. King minus man plus woman approximately equals queen. This is real. With word embeddings, you can actually do arithmetic with words. The vector for king minus the vector for man plus the vector for woman gives you a vector that's closest to queen. This shows that embeddings don't just capture individual word meanings, they capture relationships and analogies. Mind-blowing, right? All right, now let's talk about our first technique, Word2Vec. Word2Vec was developed by a team at Google in 2013, and it completely revolutionized how we create word embeddings. It's a neural network-based model that learns embeddings from large text corpora. The beautiful thing about Word2Vec is that it's unsupervised. You just feed it tons of text, and it figures out the embeddings automatically. Word2Vec has 2 main architectures. The first is CBOW, Continuous Bag of Words. CBOW predicts a target word from the surrounding context words. So if you have the sentence, the cat blank on the mat, CBOW looks at all the surrounding words, the cat on the mat, and tries to predict the missing word, which is sat. The second architecture is Skip-Gram, which does the inverse. You give it a single word like sat, and it tries to predict all the surrounding context words, the cat on the mat. Now, here's the key. As the model trains on millions and millions of these examples, it adjusts the word vectors so that words appearing in similar contexts get closer and closer together. That's how it learns meaning. Let me break down exactly how each architecture works. With CBOW, you're essentially playing a fill-in-the-blank game. The model sees the cat blank on the mat, and it needs to predict SAT. CBOW is generally faster to train and works better for frequent words because it's averaging context from multiple surrounding words. Skip-Gram flips this around. You give it one word, SAT, and it tries to predict every context word around it. Skip-Gram is typically better for rare words and achieves better semantic accuracy because it treats each context word as a separate observation. So instead of one training example, you get multiple training examples from the same window. The beautiful part? Whether you use CBOW or Skip-Gram, after training on millions of contexts across your entire corpus, you end up with these meaningful, dense vector embeddings that capture semantic relationships. Now let's shift gears and talk about GloVe, Global Vectors for Word Representation. GloVe was developed by the Stanford NLP Group in 2014, and it takes a completely different approach from Word2Vec. Instead of predicting context words like Word2Vec does, GloVe takes a more statistical approach. It starts by building something called a global word co-occurrence matrix from your entire corpus. This matrix keeps track of how often every pair of words appear together within a certain context window. So if ice and solid appear near each other frequently, that gets recorded in the matrix. Then, and this is the clever part, GloVe factorizes this matrix to extract word vectors. The goal is to create vectors that preserve all those co-occurrence statistics. Here's the core mathematical idea behind GloVe. The dot product of two word vectors should approximate the logarithm of how often those words co-occur. So if you take the vector for ice and dot it with the vector for solid, that should be close to the log of their co-occurrence count. This elegant mathematical property ensures the embeddings capture semantic relationships. Let me make this more concrete with a simple example. Imagine we're analyzing a corpus about states of matter. GloVe would build this co-occurrence matrix showing how often words appear together. Look here. Ice and solid co-occur 180 times. That's a lot. That makes sense because ice is solid. Meanwhile, ice and gas only co-occur 5 times. They're semantically distant. Similarly, steam and gas co-occur 165 times, but steam and solid only 8 times. GloVe takes this entire matrix and factorizes it to extract vectors. These vectors embed all these global co-occurrence patterns directly into the embeddings. And this is the key difference from Word2Vec. Word2Vec uses local context windows and makes predictions, while GloVe uses global statistics from the entire corpus. Both approaches work, but they capture information in different ways. All right, let's put these side by side and see how they compare. Approach. Word2Vec predicts context words locally using a neural network, while GloVe factorizes a global co-occurrence matrix. Data usage. Word2Vec uses local sliding windows as it trains, while GloVe uses statistics from the whole corpus at once. Training type. Word2Vec is neural network-based with CBOW or Skip-Gram. GloVe uses matrix factorization, a more traditional mathematical approach. What they capture. Word2Vec captures local semantic relationships from nearby words, while GloVe captures global semantic patterns from the entire corpus. Speed. Word2Vec can be faster when training on very large corpora because it processes windows incrementally. GloVe requires building the co-occurrence matrix first, which can be memory-intensive. Best use cases. Word2Vec is widely used for general NLP tasks and works great with large datasets. GloVe shines when you really need to capture global context and statistical properties. So in summary, Word2Vec is about local context prediction, while GloVe is about global statistics factorization. Both are excellent choices depending on your specific use case. Now let's get practical. I want to show you how to actually implement Word2Vec in Python using the Gensum library. First, we import the necessary libraries, Word2Vec from Gensum and the word tokenizer from NLTK. We download the Punkt tokenizer data, which helps us split text into individual words. Here's our sample text. Word embeddings are dense vector representations of words. We tokenize it into individual lowercase words. Now comes the interesting part, creating the Word2Vec model. Let me explain these parameters because they're important. Vector size equals 100 means we're creating 100-dimensional word vectors. You can use 50, 100, 200, or 300. Higher dimensions can capture more information, but require more data. Window equals 5 is the context window size. This means the model looks at 5 words before and 5 words after the target word. SG equals 1 tells the model to use Skip-Gram. If you set this to 0, it uses CBOW instead. Men count equals 1 means we include words that appear at least once. In real applications with large corpora, you'd set this higher to filter out rare words. Workers equals 4 uses 4 CPU threads for parallel training. This speeds things up. We train the model for 10 epochs, meaning it goes through the data 10 times. Then we can extract the vector for any word. Here we get the vector for a word. And we can even find similar words. The model will return the top 3 most similar words based on vector similarity. These key parameters give you a lot of control over how your embeddings are learned. Experiment with them to see what works best for your data.
Now let's look at how to use pre-trained GloVe embeddings. This is actually how most people use GloVe in practice. GloVe embeddings are typically downloaded as text files from Stanford's NLP website. The format is simple. Each line has a word followed by its vector components. Here we're using the GloVe.6b.50d model. That's GloVe trained on 6 billion tokens with 50-dimensional vectors. We load the embeddings by reading the file line by line. For each line, we split it. The first value is the word, and everything else is the vector. We convert the vector values to floating point numbers using NumPy and store them in our dictionary. Once loaded, we can instantly get the vector for any word in the vocabulary. Here, we get computer. We can also calculate cosine similarity between any 2 words to see how semantically similar they are. This function computes the dot product divided by the magnitudes, a standard similarity metric. Here we compare king and queen and get a similarity score. Higher scores mean more similar words. Stanford provides several pre-trained GloVe models. The GloVe.6b is trained on Wikipedia and GigaWord, 6 billion tokens. The GloVe.42b uses 42 billion tokens from Common Crawl, and the GloVe.840b is the massive one with 840 billion tokens. You can choose different dimensions, 50, 100, 200, or 300. Higher dimensions capture more nuance, but require more memory. The beauty is, you don't need to train these yourself. Just download and use them in your projects. Alright, so we've learned what word embeddings are and how they work. But you might be wondering, where are these actually used? Let me show you. Text classification and sentiment analysis. This is huge. You convert documents or reviews into embeddings, then feed them to machine learning models to classify them. Is this email spam? Is this review positive or negative? Embeddings make this possible. Semantic search and information retrieval. Instead of just matching keywords, you can find documents that are semantically similar. So if someone searches for car, your system can also return results about automobile or vehicle because the embeddings know these words are related. Machine translation. This is fascinating. You can align word embeddings across different languages. If you learn that cat in English and gato in Spanish have similar contexts, you can map them together for translation. Chatbots and conversational AI. Embeddings help chatbots understand what users actually mean, not just the exact words they use. This makes conversations feel more natural and intelligent. Text similarity and paraphrase detection. Measure how similar 2 pieces of text are. This is used for plagiarism detection, finding duplicate content, or matching questions to answers. Named entity recognition. Identify and classify entities like person names, organizations, locations, and dates in text. Embeddings provide the semantic understanding that makes this accurate. These are just some examples. Word embeddings are used in almost every modern NLP application. They're truly foundational. Now, as powerful as Word2Vec and GloVe are, they're not perfect. Let's talk about their limitations. This is important to understand. Limitation number 1, out-of-vocabulary words. This is a big one. If a word wasn't in the training data, there's no embedding for it, period. New words, typos, rare terms, they just can't be handled. So if your model was trained before the word cryptocurrency became popular, or if someone misspells a word, you're out of luck. This is a real problem in production systems. Limitation number 2, polysemy, multiple meanings. Here's the problem. These embeddings are static. The word bank gets exactly one vector, whether you're talking about a riverbank or a financial bank. The embedding can't change based on context. So bank in I went to the bank to deposit money has the same vector as we sat by the riverbank, even though the meanings are completely different. Limitation number 3, fixed context windows. Both Word2Vec and GloVe use relatively small context windows, typically 5 to 10 words. They can't capture long-range dependencies or understand complex relationships that span across sentences or paragraphs. So, what's the solution? Contextual embeddings. Models like BERT, GPT, and Elmo generate different embeddings for the same word depending on its context. They're dynamic, not static. BERT would give bank a different embedding in financial bank versus riverbank because it looks at the entire context. But, and this is important, Word2Vec and GloVe remain foundational. They're faster, simpler, and still incredibly useful for many applications. Plus, understanding these techniques is crucial for understanding the more advanced models that came after them. All right, let's bring all this together and summarize what we've learned. Word2Vec, developed by Google, uses a neural network approach with 2 architectures, CBOW and Skip-Gram. It learns from local context windows and predicts words from their surrounding context. It's fast to train on large corpora, works great for general NLP tasks, and has excellent libraries like Gensum that make it easy to implement. GloVe, developed by Stanford, takes a matrix factorization approach. It uses global word co-occurrence statistics from your entire corpus. It captures broad statistical relationships, excels at capturing global context, and Stanford provides widely used pre-trained models that you can download and use immediately. Here's the key takeaway. Both Word2Vec and GloVe remain foundational to natural language processing. They're the building blocks that led to more advanced models like transformers. Even though we now have BERT and GPT, understanding these techniques is essential. They're still used in production systems, they're faster and more efficient for many tasks, and the concepts you learn here apply to understanding modern architectures. If you're starting your NLP journey or building custom embeddings for your projects, master these 2 techniques first. They'll give you a solid foundation for everything else. And that's a wrap. Thank you so much for watching this deep dive into word embeddings, Word2Vec, and GloVe. I hope this video helped clarify these concepts for you. We covered what word embeddings are, why we need them, how Word2Vec and GloVe work differently, saw code examples, discussed applications, and even talked about their limitations. If you found this video helpful, please hit that like button. It really helps the channel grow and lets me know you want more content like this. Make sure to subscribe and turn on notifications so you don't miss future videos. Thanks again for watching, and I'll see you in the next video. Until then, happy coding!